This is Jeremy Jorgensen with the School of Family Life at Brigham Young University, and today I'm going to be talking about exploring growth in data, looking at longitudinal analysis specifically with the growth curve. Longitudinal analysis oftentimes starts with 2 time points, and there are 2 major types of models that people use with 2 time points. The first one is probably the most common, where we see researchers who have a repeated measure, the same thing measured at time 1 and time 2, and they use some predictors to predict time 2 of their outcome, controlling for time 1 of that outcome. And this is one way to see, okay, how do my predictors predict variance that's left over after I'm controlling for the stability of my outcome over time. Another way that researchers look at 2 time point data is to take that outcome at time 2 and subtract the time 1 score, calculating essentially a change score. And this is an interesting way of doing things. It's a way of getting at, okay, how did somebody change over time, and how are my predictors related to that? One of the challenges with change score models is that interpreting the output or interpreting the results is sometimes difficult, because sometimes people change increasing while other people change decreasing. And so a 1 unit change in X is related to this much change in Y. You see on the slide here, positive coefficients suggests that X is linked with more change in Y. I'm just reading the last part of this slide here, or the last part of this line. Or in time 1 of Y being less than time 2 of Y, because we're subtracting time 1 from time 2. I'm just thinking, got to make sure that this is straight in my mind. Again, these are tricky to interpret. A negative coefficient suggests X is linked with less change in Y. So the issue here is that a positive coefficient suggests more change, a negative coefficient suggests less change, but what it doesn't help you with is if someone's change score is positive or negative. If they're changing in a positive direction versus a negative direction. I think you get the sense. It gets more complex, and so you need to think long and hard about what your data are telling you when you use a change score model. In the literature, we see some discussion of a residualized change score model. And my understanding is that, and actually when I've run a residualized change score model and a change score model, is that I get equivalent results within an SEM framework. And so I won't talk much more about the residualized change score at this time. This is an example of the first approach where you're predicting time 2 with time 1. You notice the red arrows suggesting the stability of school engagement over time or pro-social behavior over time. In this model, we're predicting time 2 with these other predictors while controlling for time 1 in our outcome. For the change score, using the same model, only switching out time 1 and time 2 of our outcome, we would simply put in this new variable and predict it instead. David Johnson wrote a paper on two-way panel analysis and suggested that when you're studying the effects of transitions, a change score would be most appropriate. Honestly, there's people who would argue either way. So there's mixed opinions among researchers as to what's best, a change score or this predicting time 2, controlling for time 1. And so you may have to Actually, an astute reviewer and editor will probably want you to consider both. You may only present results from one in a paper, but have estimated the other model and understood what happened, and maybe even reported that model in brief. Okay, so some people extend a two-wave model beyond 2 time points by saying predicting time 5 with time 1 predictors, or predicting using an outcome at time 3 or 4 or 5 with something from time 1. That is, you could sometimes independent variables are associated with dependent variables differently depending on the amount of time that has passed. And so sometimes people might use 2 time points in a different way. Some examples of other extensions are the actor-partner independence model and a common fate model of a longitudinal model. I've got a couple of examples here. Here's a actor-partner model with depression in men and women predicting, actually this is probably husbands and wives predicting dyadic adjustment. Here we have an interesting way of thinking about an actor-partner model with an interaction between man and woman predicting satisfaction. So there are so many different extensions that you can consider. This is another actor-partner where we have husband and wife predictors, husband and wife outcomes, and with just 2 time points. Actually, this paper, I believe we only used 1 time point. Actor-partner models can use 2 time points, and again, you could use change scores, or you could predict time 2 controlling for time 1 with those. Okay, the meat of what we want to talk about today, many times we have more than 2 time points, and we want to look at not just change from one time point to another, but the development of different processes. And when we're doing this kind of work, in order to estimate a linear trend, we have to have 3 time points. And in order to estimate curves in a linear trend, we have to have at least 4 time points for a quadratic trend, 5 time points for a cubic trend, and etc. Essentially, the reason for this is because with 2 time points, the line is known, the difference or the change from A to B. With 3 time points, we actually then can estimate a line that is not known. And that's why we need 3 time points for the linear. Then for quadratic, it just extends beyond the 3 time points. So we would not use a growth curve approach for all data that has 3 or more time points. It's generally the preferred approach when our data increase or decrease systematically. That is, we see some kind of growth upward or growth downward in our data that we then can model. And I'll show an example of some data that's not appropriate for that in just a minute. Now, before we're estimating a growth curve model, it's a good idea to see what your data are like, what they look like. And this approach is taken from Singer and Willett longitudinal data analysis book that they have, where you plot your data and you check it out and see what's going on before you start modeling complex models. In SPSS, if you want to plot your data, what you would do is first change your data from a wide format to a long format. So repeated measures are not captured across a row, but rather in columns. We call this stacking our data. And so if our data looks like this, where for ID number 1, we have our predictor at time 1, our predictor at time 2, our predictor at time 3 and 4, and then our outcome at time 1, 2, 3, and 4. This would be data that's in the wide format or unstacked. And we might apply this SPSS syntax, vars to cases, making x from the x variables and making y from the y variables with 4 time points. In Stata, you would use the reshape command, and we would then see something that looks like this, where each person has four rows of data, with the time variable being what helps us to know for ID number 1, for example, which time point the x and y variables are from. So this is what the data look like when it's stacked. Once it's stacked, we can then use this syntax in SPSS here on the left and Stata here on the right. And you would change out the y with the dependent variable there in the SPSS syntax. You'd also need to make sure that the ID variable is the same, and your wave or time variable is called time. In that Stata command, we have wife's marital quality, W underscore marital quality with time and ID. So you need to make sure that these things match up in your data set, and then you should be able to run them. And once you do that, you get something that looks like this. And these are called spaghetti plots. And each line represents an individual in the data. Because there are lines that overlap, there are probably more people represented in this graph than you actually see, because some of the lines are on top of each other. But you get a clear sense of the direction that people are going in. So here, clearly we don't have just a linear effect, but we've got some kind of curve going on there around time too. Some other spaghetti plots. This is a daily diary spaghetti plot, where it looks like maybe we see quite a bit of fluctuation. Sometimes just by looking at these plots, even though they're pretty messy, we can still see patterns. Like we see a ceiling here that tends to maybe go upwards. It's a good idea to superimpose a regression line, then you can see exactly what's going on here. Here we have probably a trend that goes downwards across time. Here again we see something that probably goes systematically decreases over time. And now a growth curve, it is important to recognize that a growth curve becomes a summary statistic for a whole sample. A lot of people in the sample may be doing different things than what that mean and that intercept and slope suggest. And so it's a good idea to know what your data look like. And if there is a lot of variability, then you're going to look at the variance components of the intercept and the variance and the slope in your output to understand that. Now sometimes we see what's called stochastic change or random fluctuations in data that don't systematically increase or decrease. These are from daily diary research as well, where there really isn't a systematic change over time of increasing or decreasing. And so we might model this similarly with a longitudinal nesting, but we wouldn't necessarily model time with relation to it. And that's really a topic for another day. But if your data looks like this, then you're probably not going to be interested in a growth curve, but rather you're going to be interested in variability. So you'd set up a variability model rather than a growth curve model. Now with growth curves, what kind of research questions can we ask? We can ask, is there significant change over time? Is the mean of the slope statistically significant, either positive or negative? Do people very significantly vary in their rate of change? Is there a significant variance around that slope? Do people significantly vary in the initial levels of the construct? Is there a significant variance in the intercept, in the mean of the intercept in your model? Sometimes we want to know if there are differences in initial levels or rate of change and what accounts for those. And we can use predictors to predict intercept and slope in this case. And we also, if we have more than 3 time points, we can look to see if our change curves over time. And the way we answer these questions is using a basic regression line where our intercept represents the average for the sample at time 1, and our slope represents, our slope associated with time represents how much change occurs in the sample for a 1 unit change in time. And let's see, so having time in the equation helps us to make this a growth curve model. Okay, so the outcome is the variable that's growing. The intercept is the starting place, or the average in the sample at time 1. The rate of change in the slope is this time coefficient, and we of course need to give or put into a model the metric of time, and usually that metric is determined by when data are collected. So if they're yearly surveys, you might have 0 for time 1, 1 for 1 year later, 2 for 2 years later, 3 for 3 years later. But you might also have variable time points where somebody was given a survey at 10 months and then 15 months and then 24 months, something like that. So you could use months, you could use days, you could use years. When you change that metric of time, it's important to look at, to consider that metric, because if you have a very large metric, you could end up with a statistically significant slope that is 0. That is, a 1 unit change in X is related to statistically significant change in Y, but the metric is so large that that change in Y is very small given the metric. If you end up with a significant slope that is 0, it's a good idea to rescale your metric using some decimal points. Should give you a number that then is interpretable. And that was a little bit of a side note. We do have some error that can be estimated as part of this growth curve as well. Sometimes we see a random intercept only, but not a random slope, such as in the left side of this figure here. And sometimes we see random or variation in slopes, but people are starting at about the same place. Other times we see random intercepts where they're starting at different places, and random slopes are going in different directions. And we use the variance component of the intercept and variance component of the slope to understand these. Okay, so let's see. Here we have emotional closeness to a grandparent spaghetti plots over time. And that spaghetti plot is pretty dense. It's hard to pick up on really what's going on. If we estimate a growth curve, we get an intercept and a slope for this. Intercept 2.8, when we plot that on the y-axis at time 0, we see that 2.8 starts about right there where that red dot is. And then the slope, negative 0.08, shows us how much change we see in emotional closeness to a grandparent for 1 unit increase in time. It's a negative coefficient suggesting that the slope is downward. Now, because that's a little hard to see, it looks, let's see, it looks something like this, where slope, 1 unit change in time, and with the little red bracket there, we see a decrease in 0.08 with each unit change in time. And that's a linear slope. Just as a side note, if we look over at the variances, we see the GP int, or the intercept, has a significant amount of variance, but the slope does not. And if we look back at this plot here, people are starting, well, in very different places, but the general trend in the data is downward. Even though we do see some going up, the overall trend is downward. And again, I think this is a great example to see that these models are sometimes not perfect for the data. I mean, they give us a general idea of what's going on, but they don't always tell us what all the individuals in a sample are doing. Okay, when we put this into an SEM framework, this is what our growth curve looks like, where we have an intercept with the factor loadings constrained to be 1 across all of them. This gives us the average level for the sample at time 1. And then the slope, you'll notice the first factor loading is set at 0, and then we're going up by the metric of time that the data were collected. Here we have the observed variables for our outcome at the 4 different time points. The mean of our slope, or unstandardized coefficient B, tells us the increase or decrease. Here are weights for our factor loadings. The mean of the intercept is the mean of y when x is 0, and I think I had mentioned those things. Okay, so if we were doing this model in Amos, this is how we would set it up. Or we could ask for M+ for a diagram or some other program, I guess Stata, we could do that as well. So setting up our growth curve model in Amos, it's a good idea in Amos to use the plug-in tool for growth curves that automatically places in the system the constraints so that your model is estimated correctly. You do want to make sure the factor loadings for the slope are lined up with the data, how they are, when they were measured, the time points they were measured at. Amos also defaults with having the error variances equal across time. And so you want to change those so that they are allowed to differ. And it's common, I guess I'll say it's been common for me with the growth curve to not have necessarily stellar model fit at first. But as you then explore different patterns of growth and add predictors, generally model fit improves. Now if it's terrible model fit, then you may want to see if there's a problem. Sometimes we have a model that looks like this, where a growth curve is not made up of observed variables, but it's actually made up of latent variables that are then made up of observed variables, a second order model, if you will. When we have this, there are certain constraints that need to be in place in order for the model to be identified. First of all, in red, factor loading should be equal across time. The observed variable intercept should be equal across time. The error variances should be equal across time. And the latent variable mean should be constrained to be 0. Once you have set these constraints in place, then you will get, in this model that you see here, you will estimate the mean of F4, not having it constrained to be 0, and the mean of F5, and then you get an intercept for those latent variables and a slope for those latent variables. So that's part of the default. One of the things that people run into, if they just create their own model, say in Amos, and they don't use the plug-in tool, they'll end up, the default is for observed variable intercepts to be estimated and for latent variable means to be set at 0. And what that does is it estimates means at each of the time points, or the intercepts, but it doesn't give you the average intercept and the average slope. That might make sense to you if you've had a little bit of experience with this, but if you're setting up your model for yourself, know that that's a problem that you could run into. So use the plug-in tool if you can. Interpreting results, the unstandardized mean of the slope tells us how the outcome increases or decreases by this amount per 1 unit change in time. The mean of the intercept is the average for the outcome of the sample at time 1, and this can change when predictors are added. Regression coefficients predicting the intercept tells us that the intercept increases or decreases by this amount, by X amount per 1 unit change in the predictor. And regression coefficients predicting the slope tell us that the rate of change in our sample increases or decreases by this much per 1 unit change in the predictor variable. I recommend that you find a published article using growth curves to be able to understand what your predictor values mean in relation to a slope. And this is especially true if you end up with a quadratic or higher order slope, then what you have is a 1 unit change in x is related to this much change in the rate of change. And it gets a little more complicated. So find where someone else has talked about it, and that will help you to understand how to put words to what your model is saying. You can find some information on the internet. The UCLA website is great, and Oregon State also has a really good document there that you could look to for more information. A lot of your growth curve models are out there quite a bit, and so there's really a lot of information that you can get just on the internet. Oregon State, that's Alan Aycock's work. Okay, so here is an example. When x is 0, we have an average of 5.05, and the average slope is negative 0.05 for each unit change in time. You can graph growth curves. You can graph linear and quadratic trends, and your equations would look something like what you see on this slide. And I would plug these into an Excel file and then use the linear plot to insert a plot of your data to put into a paper. A lot of times it's nice to have a growth curve plot in your paper. And I'll say that M+ will do this for you, where you just look at a plot, and I'll show you how to do that. But those plots are not as pretty as the ones you can make in Excel. So putting this into Excel might look like this, where you have time points 0, 1, 2, and 3, and then here are your estimated means at time 0, 1, 2, and 3, and you put in a plot, and this is what it would look like. If you have a quadratic trend in your data where a linear slope is downward and then curves up, or is upward and then curves down, you might want to plot a quadratic curve, say in Excel, in which case you would take the time variable and square it, adding it to the equation. And it depends on what program you use where you would actually do this, but from a regression equation standpoint, that's what it looks like. In AMOS, you simply add another latent variable, and I've got an example here. You add a latent variable, and then you will square the factor loadings for the quadratic variable. And in M+, I'll show you how to do it. You simply add another symbol right after the slope symbol, and they automatically calculate a quadratic trend for you. Okay. When do you know if you should add a quadratic slope? Well, if your model fit significantly improves, that's a good sign. Sometimes, actually, if you don't have enough degrees of freedom, or if it is a very poor model fit, the model will simply not run when you add a quadratic slope. That's a good sign that a quadratic slope is not best for your model. But again, you want to plot your data and see what's going on to confirm that. And the mean or the variance of the quadratic slope may be significant, indicating that this is something you should look into further. Okay, some people prefer to use repeated measures ANOVA for longitudinal or repeated measures data. SEM both includes measurement error, and it provides variance parameters for the intercept and slope, which you don't get with an ANOVA approach. Most of the models we estimate in SEM can be estimated using multi-level modeling with observed variables or scales, and that is a good way to go if you have a smaller data set. SEM is a large data type of analysis, and so If you have a larger data in SEM, you're great. If you have a smaller sample, then you probably want to consider a multi-level framework. And when I say small, again, it depends on how many variables you're estimating in your model. But under 100, it's going to be tough to estimate a growth curve in an SEM framework. Okay, so I'm going to come out of PowerPoint here and start in Amos with this. This is a growth curve that's been created using the plugin, and maybe I'll just go through and show you how to do this, since it shouldn't take very long. So we'll go to plugins and we'll say do a growth curve model. Yes, we will save this, and we want 3 time points. Okay, so it's going to give us this model. Now notice that the error variance is the same for each of the time points. So we're going to call this, E1, we want the parameters variance, we'll call it variance 1, variance 2, and variance 3. Notice our intercepts, our observed variable intercepts, are set at 0 so that we can estimate the mean of the slope and mean of the intercept. That's required in order to for the model to be identified. Now, Amos has automatically set this at 0, 0.5, and 1. Now my data were collected across 3 years, so I'm going to call it 0, 1, and 2. Okay, and now I also need to bring in the variables. Let's see. That is not the right data set. I should have thought this was going to just transfer right over. And we don't want stacked. Let's see. Well, let's use this one. And let's see, okay. So I put in time 1 marital quality, time 2 marital quality, and time 3 marital quality. And I run that. It's going to save under, let's call it MQLGM. And now I'm going to go straight to the output here. Default model OK tells me that it ran. I would normally look at model fit. Well, minimum was achieved also tells me it ran. Normally would look at model fit before I interpret any outcomes or any of my data. For the sake of time, I'm just going to go straight to the intercept and slope means by clicking on estimates here. And let's see, here's my mean for my intercept, 5.25, with a slope of 0.057. That's a positive slope. And these are both statistically significant, meaning the intercept is different from 0, no big surprise. The slope is also different from 0, going in an upward fashion. When I look at my intercept variance, I see that that is also significant, and my slope variance is not statistically significant. So people are pretty much generally going upward in this data set. with the specific variable. And however, there is variability in terms of where they start. Okay, so that's how we would set it up in AMOS. I'll go ahead to M+ now, where we have this data is grandparent closeness across 3 different years. And the way we set this up is we say model I represents the intercept, S represents the slope. You could put anything here. Whatever comes before this line in M+ is the intercept and slope. If I had 4 data points, I could add something else here, like a Q, and that would estimate a quadratic slope as well. I don't have 4 data points, so I'm not going to do that. But if I were to run this, I get my output, and right here for my means, I have an average of 2.778 at time 1 with a downward slope of 0.086. If I go to the variances, we see that I have a significant amount of variance, but not a significant amount of variance in the slope. So a significant amount of variance around the intercept, but not around the slope. I could expand this model to a model with latent variables. So this is that higher order model where I've got factor loadings constrained across time, intercepts constrained across time, and error variances constrained across time. And then I also have the means of the latent variables at the higher order set at 0, so that the intercept and slope here the means of those can be estimated. I'll go ahead and run that. And just for fun, let's take a look at the diagram, see what M+ tells us this model looks like. Let's see. Not sure if that worked or if it didn't work. Let's try one more time. If it doesn't work, we'll just move on. Okay, I'm not getting a diagram there. I will go also to the plots. Here we can plot the estimated means. There are a number of other plots we can do. This is the one that you normally would do with a growth curve, where you could see, okay, my intercept is 0.235 or something like that with a downward slope across time. And if we go down to our output, we see that the intercept, okay, actually that intercept is set at 0 with a downward slope. So I wonder why M+ plotted that at 0.235. If we go down to the variance components here, we do have a significant amount of variance in the intercept and the slope with this data. I wanted to show a couple other examples. This example has 4 time points. Now in M+, I think I forgot to mention this before, instead of factor loadings for the slope, we put the variable for time 1 and then we say at 0, and that's basically setting the factor loading. At 3, at 8, at 16. And notice, well, I've got a Q here. I'm going to estimate a model with an intercept and slope first. And we'll run this. Oops. With our mean at 1.76 and a slope of 0.001 that's not significant, we do see a significant amount of variance around the intercept and slope in this model. Let's see if we can plot the observed individual values will give you a spaghetti plot, and we have to tell it how many we want, like 100, and see maybe we see a downward trend here. We can also view the diagram of this model, which is going to look a lot like the one in Amos. Now, the slope, notice there's no factor loading going to time 1. And another way to say that this is 0, to set that factor loading at 0, is to simply leave it out. And that's what M+ has done here. And then 3, 8, and 16 is our time metric across time for this example. So this suggests that, let me see, that this model is specifically with marital quality. So the average is 1.763 at time 1, and it's essentially flat across time, which those observed variables suggested. Let's see, let me do one more example here. This is a dual growth curve, so we have wife, intercept, slope, and quadratic, husband, intercept, slope, and quadratic. I should have added a quadratic to that last one that we were looking at, but let's run this one and see what we get. So we have an intercept for wives of 5,110, and for husbands of 5,181. And we could test whether these are statistically different or not. The slope for wives is negative 0.13, and for husbands negative 0.12 essentially. And then we have a quadratic, significant quadratic slope that's upward. So what we have is starting at 5,1, going down, and then going back up. I wonder if it will let us plot the estimated means. We should be getting one for husbands and for wives here. I don't know if there's a way. Let's see. I don't think this is really what we're looking for. This is our observed and estimated means. They're pretty similar. We're seeing this little dip right there. That might be that initial downward and then flattening. We could plot this in Excel and maybe get a picture that helps us out a little bit more. When we go down to the variance components, we have a significant variance in the intercept for husbands and wives, but no significant variance in the slope or quadratic slope. A lot of times when there's variance in slopes, when you add a quadratic term, it accounts for that variance, and so the slope variance is no longer significant. So those are the examples that I wanted to show you. There are so many different extensions of growth curves, and I do have another lecture that's recorded adding time varying and time invariant predictors to growth curves, and as well as to a quadratic growth curve. So you can check out that video if you like. I've gone over just a lot of the bare bones basics, haven't got into a lot of depth with this. A really good book is the Duncan Stryker book on growth curves. I recommend that, and good luck as you explore and then model your data over time. Thank you very much.